Alright, welcome to problem set 19. So all of these questions, there's only 5 of them I believe, but they're all pretty long, so we'll take our time working through it, but they're all pretty much the same. Just some are a little harder than others because of how complicated the function itself is, but we will work on that. So number 1 here, it says f of x equals x cubed plus 2x plus 8. The first thing we want to find is the y-intercept. That's really easy, right? That's just whenever this equals 0. We see that there's a y-intercept at... Oh, whoa, I don't know why I did that. That was startling. So y-intercept at 8, right? Because if I plug in the 0 there, that equals 0 at 8. So y-intercept is... Why is it doing that? I don't... That's unusual. It hasn't done that before. It's because I'm trying to write on the page. That's... What? Okay. Okay. I'm just going to write stuff next to it. Okay, there we go. I don't know what to do. I'm just... Okay. We're going to write it over here. Our y-intercept is at 8, 0. And, yeah, I can... No, sorry. 0, 8. I got that all mixed up. Right, because our y-intercept is going to be wherever we cross here, which is going to be when x equals 0. So our y-intercept is up here, because if x equals 0, we've just got an 8 left over. Oops. Okay. Next up, our graph is symmetric with respect to which axis? So there's a couple ways we could do this. First, we could just kind of sketch out the graph and visualize it and kind of just see what's going on. But we want to figure this out algebraically, just so that we know how. So it can either be symmetric with respect to the y-axis, the origin, or no axis. And it will be symmetric with respect to the y-axis if it's an even function, and the origin if it's an odd function. So algebraically figuring out if it is an even function, that's going to be the case when this is true. So let's go ahead and test that out. So a negative x in here would be negative x cubed, which would just be, yeah, so negative x cubed plus 2 times the negative x plus 8, and that's just going to be the same thing as this, which is not our original function. So we see that it's not an even function here. So let's see if it's an odd function now. To test if it's an odd function, that's going to be the case when this is true. So even, odd. Okay. And so now we plug that in there. So again, plug in that negative x. And that's going to be, so f of negative x equals negative x cubed minus 2x, but still plus an 8. Oops, that's going to be that. A negative of the applied to the whole function would be this, which is not equal to this. So these are not, this function is not symmetric with respect to either axis. So neither. Next, we want to find our relative minimums and maximums. So we want to take the derivative, of course. We've got our f of x equals x cubed plus 2x plus 8. Our derivative, nice and simple, is just going to be like so. And then our second derivative is that. Okay, and I see that my first derivative is going to equal 0. whenever this equals 0. So it's going to be x squared, or 3x squared equals negative 2, if I subtract this 2 off from both sides. X squared equals negative 2/3. Well, now if I take that square root, I'm going to have a negative in my square root, which is an imaginary number. So we don't actually have any critical points here. No critical points because they're imaginary and therefore outside of the domain. No critical points. So now we check for our second derivative. This equals 0 when x equals 0. So we still want to take a look at our intervals, of course, except now we've just got two simple ones. We can check, let's see, we'll check if we're increasing and decreasing on each one. So if I plug in a negative 1 to that first derivative, that's going to get 3 times 1 plus 2, which is 5, which is positive, so we are increasing. And then if I plug in a positive 1, it's going to get me the same thing. So it's positive and increasing the entire time. Let's plug in those values for our second derivative as well, just to figure out the concavity on these intervals. So if I plug in a negative 1, that's going to be a negative 6, which is less than 0, meaning that it is concave down. And then if I plug in this, we're going to get a positive 6, so it is concave up, which means that our function, it's increasing the whole way, but it's concave down, which means it probably looks something like that, maybe. But it's just to give us an idea of what's going on there. So now we see that we don't have any relative minimums, right? Because 0 is not a critical point, it's an inflection point. And we've got no other points on here that could be a relative minimum or a maximum, so all of that's going to be D and E. They do not exist. Okay. And next up it asks on what intervals is the function increasing? Well, we figured that out. It's going to be increasing the entire way, right? It's going to be increasing from negative infinity all the way to positive infinity. And it is concave downward from negative infinity up to 0 with an inflection point at x equals 0. Now we want to see if there are any vertical asymptotes. So a vertical asymptote is whenever our denominator is 0 or undefined, with the exception of any holes, of course. Obviously, we don't have a denominator here, so we can pretty blatantly say just there are no vertical asymptotes. Now we're going to check for horizontal asymptotes, which is a similar deal, right? We typically can figure that out with rational functions, but this is just a polynomial with nothing in the bottom. And so we can say that there is no horizontal asymptote. Okay. On to the next one. Same deal, different function. So f of x equals this. We first want to find our y-intercept. Obviously, if I plug in an x equals 0 here, it's just going to be 0. So our y-intercept is at 0, 0. Now we want to figure out which axis it is symmetric with respect to. So again, I want to see if it is even, which means that. Let's go ahead and plug that in. If I have negative x in there, I'm going to have 8 negative x squared minus negative x to the 4th, and obviously when I square it, that's just going to be positive, so it's going to end up the same as this, and the same thing there. So this is equal to our original function, so it is even, which means it's symmetric with respect to the y-axis. Next up, we've got our relative extrema. So again, we've got our function here. Next, we take our first and second derivatives. These are nice and easy for us. So let's see, we're going to get this And I am going to just factor out that 4x because it makes it a little easier to see when it equals 0, right? Okay. And then our second derivative is going to be 16 minus 12x squared. Okay. And I only factored this out just because smaller numbers are a little easier to work with. Okay. So I see that this is going to equal 0 whenever x equals 0. Or let's see, if I've got 4 minus x squared equals 0, that's going to be negative x squared equals negative 4, or just x squared equals 4. So x is going to be plus or minus 2. Next up, we see that our second derivative equals 0 whenever this equals 0. So obviously it's going to be that x squared equals 4/3. So x is going to equal plus or minus the square root of 4/3. I could also write the square root as it's the same as plus or minus 2 times the square root of 1/3, or plus or minus 2 over the square root of 3. Those are all different ways I could write this. These mean the exact same thing. Just writing it different ways, though, can help you get a better idea of what that number is if you obviously just don't know the square root off the top of your head. So I know that the square root of 3 is a little bigger than 1, but it's less than 2, which means that this is going to be bigger than 1, but less than 2. So I'm just going to make a note of that for myself. It's bigger than 1, but less than 2. This helps us when picking out values to test inside of our intervals, right? So now, put together our intervals. I'm basically going to start at negative infinity. And then, since this is less than 2, it's going to come after this here. So I'm going to have negative 2, because that's further in the negatives, and then negative 2 up to that negative square root. Then I've got the negative square root. Oh, messed up writing that. Let's try that again. Negative square root up to 0. 0 up to the positive square root there. And then my positive square root up to 2. And then 2 up to infinity. Okay, so we've got a lot to test here. Let's go ahead. We'll start with that first derivative. So I can test, let's see, plug in a negative 3 maybe here. And I can know that this is going to be a negative 12. And then if I've got a negative 3 squared, that's going to be 9. 4 minus 9 is negative 5. So it's negative. A times a negative is positive. It's greater than 0. So we are increasing. Let's try another one. This one's tricky just because we don't know a whole lot more about this. I'm going to assume that this is less than 1.5, but I'm also going to double check that with my calculator because I don't want to be wrong and then mess up the problem there. Yeah, it is less than 1.5 because it's something like this. Okay, so it's less than 1.5, so I can plug in a 1.5 here, or a negative 1.5 rather. And that's going to be a negative on that outside, times, let's see, 1.5 squared. 15 times 15 is 225, so it's going to be about 2.25. That's going to be positive. This is less than 0, and we are decreasing. Okay. Next up, though this is less than 2, but greater than 1, so I can plug in a negative 1 in there. And that's going to be a negative and a positive, still decreasing. Now I can plug in a positive 1. That's going to be a positive and a positive, which is increasing. Plug in a positive 1.5, which is also positive and positive, so increasing. Now we'll plug in a positive 3 here. So that's going to be positive 12 on the outside there, and then it's going to be 4 minus 9 again, so it's a negative, and we are decreasing. Okay, now we just want to test, I'm going to erase this bit here. Now we're just going to test our concavity. So I'm going to use probably the same values for these here. So if I plug in a negative 3 here, that's going to be, well, that would be a positive 9 times the 3 is 27. 4 minus 27 is negative. So this is less than 0, so it's concave down. Plug in a negative 1.5. Again, that was about 2.25 times 3 is going to be bigger than 4, so it's also going to be less than 0, concave down. Plug in our negative 1. 4 minus 3 times 1 is positive, so we are concave up. Positive 1 now, same deal. It's going to be greater than 0, concave up. Then if I plug in a positive 1.5, I'm going to have the same result as up here, right? Because that's squared. So that's going to be less than 0. And then finally, positive 3 is also less than 0. So this is what our concavity looks like. So let's take a look at our critical points here. So I see that it's concave down and it's increasing and then decreasing right up to here. So this is going to be a relative maximum. Just make a little note for ourselves. 0 is another 1 and it's not an inflection point. So that looks like it's probably a minimum based on this concavity, and it's decreasing and increasing. Yep. So that's a relative minimum. And then 2 looks to be another relative maximum off of that. So we know our relative minimum is at 0, and it's going to be 0, 0 if I plug that in. We don't have any other minimums. We have a relative maximum at negative 2 and 2. And now I just plug that back into the function. So if I have 8 times negative 2 squared, that's going to be 8 times 4, that's going to be then minus negative 2 to the 4th. Let's see, 2 to the 3rd is 8, 2 to the 4th is 16, so that's 32 minus 16 is 16. And because of these here that cancel out that negative, I know that I'm going to get the same answer when I plug in my positive 2, so that's what we get there. And then we've already figured out on what intervals it's decreasing, right? So it's decreasing here to here, and then here. So let's see, that's a negative 2 up to 0. Negative 2 up to 0, and then also 2 up to infinity, okay? And then it is concave upward. Oh, that's a separate question. It's concave upward on this interval. I'll use green, it stands out a little more. This interval. And this interval alone, so that's just going to be from here all the way up to the positive 1. Okay. And we know we've got inflection points at plus or minus the square root of 4/3. Again, we don't have any vertical asymptotes because we don't have a denominator, and same deal with our horizontal asymptotes. I don't see any reason for us to have something there. Okay. Now for question 3. This one's a little bit more complicated. So it says g of x equals 8x over 1 plus 4x squared. So we know when we take the derivative, we're going to have to use quotient rule. It's going to be a little ugly. Right off the bat, we want to figure out our y-intercept. So if I plug in an x equals 0, I'm going to get a 0 up top and just a 1 in the bottom. So our y-intercept is at 0, 0. Okay. Now we want to see if it is even or odd. So we first test for even. I suppose it doesn't really matter which order we do it in, but if I plug in a negative x, it's going to be negative 8x, and nothing changes in the bottom, so that's not the same as our original function, so it's not even. Let's check if it is odd now, which means that this must equal this. So if I plug in, again, that negative x, suppose I didn't have to erase it because it kind of already did it there, over this. Well, this is odd, right? Because if I just apply a negative to this whole thing, it's really only going to matter onto that numerator. So this is odd. It is an odd function, which means that it is symmetric with respect to the origin. Okay, next up is relative extrema once again. So we're going to go ahead and take that first derivative. And again, this is going to be a little ugly. So remember, quotient rules, low d high minus high d low over low low. So it's going to be 1 plus 4x squared times the derivative of 8x, which is just 8, minus 8x times the derivative of the bottom, which is going to be another 8x, all over the bottom squared. And I know since we're going to take the second derivative, I'm pretty confident that something's going to cancel out, so I'm going to leave these in these similar terms here, but I will distribute that little bit out, so it's going to be this here, or actually I will distribute that 8 just for convenience sake. So it's going to be 8 plus 32x squared minus, this will be a 64x squared all over, oops, I forgot my squared. Okay, all over this. And I can combine like terms. So that's going to be a negative 32x squared because of these terms here, plus 8 over that. And I will just factor that out to make it a little easier to work with. I'm going to factor out an 8. So it's going to be a negative 4x squared plus 1. I keep forgetting these squares in the bottom. So this is our derivative, our first derivative there. And now I'm going to use this one just because it's a little easier to figure out the second derivative. Once again, quotient rule, low d high minus high d low. So we take our low term, which is, oops, this, times the derivative of our top, which is going to be a negative 64x minus that top bit times the derivative of our bottom. We want to use chain rule there, so the derivative of the outside is going to be 2 times the inside times the derivative of the inside, which is going to be an 8x. Obviously, I can combine the 2 and the 8x to be a 16x, like so. And then our bottom is squared again, so square to the square is going to be to the 4th. And I see that I've got this term twice in here, so I can factor that out. Okay, so it's going to be like so. Obviously this one still remains because this is squared and I'm only factoring 1 out. Minus 32x squared plus 8 times, this is now factored out, so it's just this here, all over, I see one of these cancels, and that's going to become these are a lot of writing, I don't love it. This here, and now instead of to the 4th, it's to the 3rd down here. And I'm going to go ahead and distribute and combine any like terms now. So this first bit is going to be negative 64x minus 64 times 4 is, I think, 256. So minus 256 x cubed, and then don't forget to distribute this negative, but then it's going to be like so. So it's going to be minus, oh, I do not know what 32 times 16 is. Oh, actually, I'm going to go backwards a little bit. I'm going to undo that. I see that I can factor out at least an 8 out of all of this, right? I can factor out 8 here, and 8 here. So I'm going to do that to make it a little easier on myself. So it's an 8, and then this is going to become a negative 8x, which makes this multiplication a little easier. So it's going to be distribute that, so it's negative 8x minus 32x cubed. And now if I'm factoring out an 8, this is going to become a 4x squared plus 1. Or wait a second. And then I can still factor out an 8. Ah! Tricky. Okay, because I can factor out an 8 from here and then another 8 from here. So this will become 4x squared plus 1. And this will become then a 2x, which means I'm actually factoring out a 64. So this will just become a negative x. So now we distribute. So I'm going to factor out 64. That's going to be negative x minus 4x cubed. Now we distribute these along with our negative. So minus 8x cubed. And still distributing that negative, so minus 2x. Okay. I think that that's right. I really hope that I didn't mess that up anywhere. Now I can combine like terms. These are like terms, and these are like terms. So it becomes, let's see, negative x and negative 2x. Or I'll combine these first, so that's going to be negative 12x cubed minus 3x. And oh, look, I can factor out even more. And we don't have to, of course, but it just makes it a little bit easier to work with, especially when we're solving for zeros. So then if I can factor out a 3x from here. So 3 times 164 is 196, I think. 64, 128, 64, yeah. 196. No, 192. 192, because I'm factoring out that 3, and then an x. And then that's going to be a negative 4x squared minus 1. Which, see how that makes it easier for us to figure out our zeros? Yeah, we see that our denominator is never going to be negative or 0 because of this square there. So right off the bat, I say that like I'm not going to have any vertical asymptotes because there's at no point that that's going to be 0 or undefined. Okay. And now I see, let's see, what was our first derivative is up here. So we want to find our critical points by setting that equal to 0. So we know it's going to be equal to 0 whenever this top bit equals 0 here, which is going to get, or just, so x equals plus or minus the square root of 1/4, which is just 1/2. So that's our critical points. Okay. And now our inflection points. Well, I see that it's going to equal 0 up here whenever x equals 0, or whenever this bit equals 0, which is going to be positive 1. Make sure to follow those signs, because this is going to end up giving me this, which if I then take that square root, because it's a negative, that's an imaginary number, so we don't include it because that's outside of our domain. So it's just inflection point at x equals 0. Okay, now I'm gonna, well, we can do it over here so we can see it all a little. Or actually, I'll just rewrite my derivatives over here so it's a little easier. So I've got my first derivative is this. And my second derivative is this. Okay. And then our critical points and our inflection point is at 0. So our intervals are going to be negative infinity up to negative 1/2, -1/2 up to that inflection point of 0, 0 up to +1/2, and then 1/2 up to infinity. Okay. Okay, now we can figure this out. So I'm going to plug in maybe a -1 here. It's nice and easy. So it's going to be obviously an 8. That's not going to change anything, so it just matters on this inside here. And our denominator is always going to be positive for all of these, so no concerns there. So that's going to be on top. That's if I plug in a -1, it's going to be -4 times 1, which is just -4. -4 plus 1 is -3, which is negative. So we are decreasing on this interval. If I plug in maybe a -1/4 is going to be on this interval. Well, it's going to be x squared, which is going to be 1/16. So I'm going to have 4 over 16, or -4 over 16, which then is just -1/4. -1/4 plus 1 is obviously going to be positive, so we are increasing here. Okay. Keep going. Now we're going to plug in a +1/4, and obviously this doesn't change anything. It's still going to get what we just got because it gets squared. So this is going to become 1/16. -4 over 16 is 1/4. Or -1/4, -1/4 minus or plus 1 is positive. We are increasing. And then if I plug in maybe a +1, we get that same -3 up in there. So we are decreasing again. Now I want to check for concavity. So I'm going to plug in these same points to, oh, that's just a -1 into my second derivative. So if I plug in a -1, I have a negative on the outside, obviously, because negative there. And on my inside, that's going to be -4 minus 1 is also negative, so that's positive. So we're concave up. Next up, so it becomes positive. Next up, we're going to plug in that -1/4, which is negative on the outside. But then in here, I'm going to get -4 over 16, so it's -1/4 minus 1, which is also negative. So again, it turns positive. We are concave up. Keep going. If I use a +1/4, well, my outside there is going to be a positive, but now my inside is going to be the same as it just was. So the whole thing's negative. We are concave down. And then we plug in a +1. We get a positive on the outside and a negative on the inside. Concave down again. Okay. So what that tells me here is obviously I'm decreasing, increasing, and this is critical point. And that makes sense. It is concave down or concave up. So that is a minimum. Our inflection point was 0, right? That's not a critical point. And then our other critical point is 1/2, which looks to be a maximum. So now it asks for those. Our relative minimum is at -1/2, and then we don't have another. Then we have a relative maximum at +1/2, and then we don't have another. And then, of course, I would just figure out what goes here by plugging that into the original function. I'm not going to do that, though, because this is a lot of writing, and I have a wrist injury, so writing this much is actually a little painful. So I'm just not going to write that for right now, just to go a little easier on myself. Sorry. And then we just see it's increasing on this bit, so -1/2 up to 1/2. It is concave upward on this bit, so -infinity up to 0 with an inflection point at x equals 0, which I think if I plug that into the original function, that's going to be, so it's going to be that 0, 0 if we want the full point. And then we just need to check for any horizontal asymptotes. Well, remember our rules for horizontal asymptotes. I've got, so 8x over 1 plus 4x squared is our original function. I see that my highest power down here is larger than this. which tells me that there is no horizontal asymptote. I believe. Let me just double check that really quick. I think that should be right. That makes sense, doesn't it? Oops. Sorry, I opened my phone and it was playing a video. I just really want to double check that because I always mix up my horizontal asymptote rules. Okay, so if the degree in the numerator is less than the degree in the denominator, then it is not none. It is asymptote at y equals 0. That makes more sense. Okay. I was really stuck there for a second. I thought I was just thinking the wrong thing, and I was. Okay, we've got 2 more questions. They're a little shorter, but the second question, or the 5th one here is a monster. Just to deal with those derivatives, really. But let's go ahead here. I've got h of x equals 3x to the 6th minus 8x to the 5th. Notice they don't ask us about our axis of symmetry, so we don't care if it's an even or an odd function. We can just go ahead and take our derivatives to find those extrema. So it's going to be an 18x to the 5th minus, I don't know about that. Actually, to make it a little easier on myself, I'm going to factor out that 3. So it's just this, which makes it a little easier because obviously this is a constant coefficient, so I can just pull it out and it doesn't affect my derivative at all. So now I can just take the derivative of that inside. So that's going to be 6x to the 5th minus 30x. It's a little easier to multiply, or 30x to the 4th. And now I can factor out a 6 from here. So it's going to be a 6 times a 3, 18, and that's going to be that. And now we can take the second derivative the same way. So I've got an 18 out there, x to the 5th, or sorry, taking the derivative, so 5x to the 4th minus 20x to the 3rd, and now I can factor out a 5. So 5 times 18, 5 times 10 is 50, plus 40 is 90. Now I've got this. And I could actually, to make our zeros a little easier, I can factor out those x's as well. So I'm going to factor out next to the 4th there. So now I've just got that for my first derivative, and then next to the 3rd here. Boom. Which again helps us just find those zeros a little easier. So our first derivative is going to equal 0, obviously, whenever x equals 0 there, or when x equals 5. And then our second derivative also has an inflection point also when x equals 0 and when x equals 4. Okay, so our intervals are going to look like this. Okay, now I'm going to plug in. So this is an h, so an h prime of, let's say -1 for that because it's nice and easy. It's going to be positive on that outside and negative on that inside because -1 minus 5 is just -6. So it is decreasing here because it's negative overall. Then we'll plug in maybe a +1 here. So I'm going to get positive on the outside, and I'm going to get 1 minus 5 is -4, so it's still decreasing. And then we'll plug in maybe a 4.5, a 4.5. So obviously it's positive on the outside, and then it's 4.5 minus 5 is still negative, so we're still decreasing. Crazy. And then plug in maybe a 6 here. So it's going to be positive on the outside, and then 6 minus 5 is +1. And we're finally increasing. Okay. Now we need to test for concavity. So I'm going to plug in these same values into my second derivative. So I'm going to get a negative out there because that's cute. And then negative 1 minus 4 is negative 5. So this is positive, which means we are concave up. Keep going, plug in that positive 1. I'm going to get positive on the outside and negative on the inside. Concave down. Plug in a 4.5 there. Positive on the outside, positive on the inside, because 4.5 minus 4 is just 1/2. And then plug in that 6 maybe. Going to get positive on the outside, positive on the inside. Boom. Okay, so we have inflection points at 0, 0, and 4, whatever that is, because that's, I don't want to plug that in, frankly. I would recommend using a calculator for plugging in our points to there. And then we have, let's see, so 0 is also an inflection point, so it's not going to be actually a maximum or minimum. So our only relative extreme point is going to be when x equals 5. So now I just got to see is that it's decreasing and increasing, and it's concave upward, so that looks like a minimum. So we have no maximums. And we only have one minimum. And that is at x equals 5. And then again, just plug that into there. And then we want to know on what intervals is it concave upward. Well, that's going to be all of this. So it's going to be negative infinity up to 0, union 4 up to infinity. Okay. And now for our last one, this is going to be painful. So again, we don't have to worry about whether it's even or odd because we're not asking about that axis of symmetry. But I'm just coming over here to give us lots of space because I know that this is going to be long. So in this case, we have to use both our product rule and our chain rule. So first, our product rule is derivative of the first times the second term plus the first term times the derivative of the second term. So that first derivative, I can take the derivative of the first, which is just 1, times our second term, and that becomes this, and then plus our first term times the derivative of our second term. Well, this is the same as that. So I'm going to take the derivative of my outside, which is going to be 1/2 times, of course, my inside, and subtract that power, and then all times the derivative of our inside, which is a negative 2x. Now, obviously that's going to cancel, so it's just going to be a negative x times this, which means that this is going on the denominator. Okay, and we're multiplying it with this, so I see that that x and that negative x are actually going to multiply to be negative x squared. Okay, and there we go, that's that first derivative, but we do want to simplify it as much as possible. So what I'm going to do is I'm going to find a common denominator here, so I'm going to multiply these together. Oops. So when I multiply this with this, obviously it cancels out the square root. So it's going to be just a 4 minus x squared, and then minus that x squared all over, because that's me finding a common denominator. This here, which is then just negative 2x squared plus 4 over that. So that's our first derivative. The second derivative is where it gets really ugly. There we go. Okay. And now knowing that, we need to use quotient rule because we've got a quotient as well as chain rule. So remember, quotient rule is low d high minus high d low over low low. I am going to turn this into that just to make it a little easier to read and recognize when things cancel out. There's a very similar problem that, like this that I went over in another video for taking that derivative. So I would go check that out as well, but that does not go over all of this bit here, I don't think. But okay, so this is our first derivative. Low d high, so we're going to take our low term. I'm going to write it over here. Our low term times the derivative of our high term, which is just going to be negative 4x, minus our high term times the derivative of our low term. And we do know the derivative of this because we took it right there. And we got that that was, let's see, let me just rewrite that out for us. We got that the derivative of this is a negative x over that square root. Or I will, like I said, I will rewrite it like this. Okay, so now derivative of our low term is going to be just that. Okay, and then all over our low term squared, and I'm just going to rewrite it like this so it's a little easier to see when I start canceling things. Because now I see I've got this term in both of these, but this makes it a little weird because that's a negative 1/2, right? But I'm going to try and factor that out. So I'm going to bring that to the outside, and now there's not one there, so it's just negative 4x minus that there plus 4 times negative x. And so it's important to see what's happening here is if I want to maybe rewrite this, so it's going to be, remember when we multiply, we are adding our exponents. So I know it's going to be, I want to factor this out. So I'm taking this out, which means that this has to be this multiplied by something else, which is going to be what's left, right? So if I need to add an exponent to this to get it here, I know that I'm just subtracting 1. So when I factor this out from this, I'm going to be left with this, or just 1 over that, right? So now I can put that right down there. And now I've factored out this bit, and I see I've got 2 of them down here. Still gotta write that out. And now I can cancel that. So now, and I am going to go ahead and distribute that, I think, as I'm writing this. So it's going to be negative 4x, and then distribute that. It's going to be minus, that's going to be a positive 2x cubed minus 4x over this, all over just one of these. Okay. And now if I just distribute that negative, that's going to be that, right? So I can take off those parentheses. Oops, I just erased my negative. Okay. And now, of course, make it easy, find a common denominator here. So I'm going to just multiply this by this so that it's all in the same bit there. So 4, it's going to be negative 16x, and then plus 4x cubed minus 2x cubed plus 4x, because now we're in this numerator because I found a common denominator, all over this, which remember is just the same as, oops, right? Because to the first power, remember we just add those exponents, so that's the same as having these multiplied together. So I'm going to write it like that just to make it a little clearer for us. And then all over this to the 1/2. That's the same as just multiplying by 1 over this. And of course you just multiply straight across, so this gets multiplied with this. And if I've got 1/2, 1/2, 1/2, I add those up, and now it is the 3/2. And then my numerator becomes this. I'm going to combine like terms here, so 4x cubed minus 2x cubed is 2x cubed, and then negative 16x plus 4x is negative 12x. So there's our second derivative. I told you that was kind of a lot. So it's going to be 2x cubed minus 12x over 4 minus x squared to the 3/2. Okay. I'm gonna go ahead and erase all this. Okay. And come back over here now that we know those derivatives. I am gonna rewrite them. I'm gonna rewrite that first derivative. I'm gonna factor out the 2. Just to make it a little, not a big thing, of course, but just make it a little easier to look at. Okay. And then our second derivative, I'm going to factor out a 2x. Okay. Now I'm going to set these equal to 0, but first we want to take a look at our domain. And I see, obviously, we've got a radical in there. So this radical, the inside of this can never be negative. That's going to be outside of our domain. And so I see what would make it negative is if x equals 4 or negative 4. So what that tells me is that for our domain, I know x needs to be less than 4 or greater than negative 4. So if we have any critical points or inflection points outside of that domain, we can't care about them. We can't use them. And I'm going to actually just rewrite that over here where it's a little easier to see. Okay, just make that a little note for ourselves. So now, if I set this equal to 0, obviously I see that that's going to be wherever that is. So negative x squared equals negative 2, x squared equals 2. So that is when x equals plus or minus the square root of 2. Okay, and that's within our domain, so that's good. And then this equals 0 at either x equals 0 or x squared equals 6. So x equals plus or minus the square root of 6. That might be in our domain. I'm going to double check that. That is in our domain, luckily, because that's a little bit bigger than 2. So obviously I'm just going to make a note for myself that that's going to be greater than 1. And less than 2, and this is greater than 2 and less than 3. Okay, so now we can go ahead and come up with our intervals. So I've got negative infinity. Obviously this is bigger than this, so it's going to be negative square root of 6, negative square root of 6 up to negative square root of 2, up to 0, positive square root of 2, positive square root of 6, up to infinity. Okay. And now we just need to plug in values. So let's take that first derivative. See, I know that it's less than 3, so I can use a negative 3 here. That's going to be 2. Negative 3 squared is 9. Negative 9 plus 2 is negative, so it is decreasing. Then I can use a 2 here, because neither of those are equal to 2. But 2 is between them, I see. So I'm going to use a negative 2. That's going to be negative 4 plus 2 is negative, still decreasing. Now I'm going to use a negative 1. Negative 1 squared. So negative 1 plus 2 is a positive 1. So we're increasing there. If I use a positive 1 for my derivative, I'm going to get the same thing. Increasing there. Now plug in a positive 2. We're going to get negative 4 plus 2 is negative, decreasing. And a positive 3 is also going to be negative and decreasing. Okay, now I just plug it into our second derivative. So again, negative 3. That's going to be a negative on our outside there. Then 3 squared is 9. 9 minus 6 is positive. So this turns out negative altogether, which means it is concave down. Plug in a negative 2, and I've got a negative on the outside, and now it's a negative, now it's a 4 minus 6, which is negative 2, which turns out to be positive, so we're concave up. Plug in a negative 1, again negative outside, again negative inside, concave up. Plug in a positive 1. Now I've got a positive outside, but a negative inside, so it's going to be negative overall, concave down. Plug in a positive 2, I've got a positive outside and a negative inside. Concave down, and I plug in a positive 3. So I've got a positive outside and a positive inside, concave up. Alright, so now again our inflection points were these here. Not our inflection points, our critical points were here. Our inflection points were the square roots of 6. So now I see that I'm decreasing and then increasing, and it's concave up. So this looks like it is a minimum, and this one looks like it is a maximum. So I only have one of each. I'm going to go ahead and put Danny in the other spots. Okay, so I've got a relative minimum at negative square roots of 2, and a relative maximum at positive square roots of 2. We have an inflection point at x equals plus or minus square root of 6, and it's concave up from here and here. So negative square root of 6 up to 0, right, because that just continues through, and then union square root of 6 up to infinity. Okay, now all we have to do is plug in these points into our original function and figure out what our relative minimum and relative maximum actually are. So if I plug in, oops, it won't let me do it. It won't let me click the pen. Okay, so now if I have this here, that's going to be obviously negative square root of 2 on the outside, and then times 4 minus, well, square root of negative square root of 2 is just 2, which turns this into negative square roots of 2 times square root of 2. Those square roots cancel out, and it just becomes negative 2. And if I plug in a positive 2, or a positive square root of 2, I'm going to get a positive square root of 2 out front. Same deal inside my radical, so it becomes this. My square roots cancel out, and it just becomes 2. And boom, we're all done. So that was our last question here. Yeah, I hope that all of these made sense. I know this was pretty repetitive. It was all pretty much the same stuff. But I figured we might need a little bit of help on that last derivative in particular, so I didn't want to skip anything. But yeah, so that is it for this problem set, and I hope that this made sense and was helpful. Thank you for watching.